Imagine a train, no engine, no fuel, no wheels on the ground, silently rocketing through a mountain at 603 kilometers per hour. Not in a science fiction film, not in a prototype lab, on a real track, in Japan, right now. The project is called the Maglev, the Linear Chuo Shinkansen, and at over $72 billion, it is the most expensive railway ever built in human history. A line that started with a $9 billion budget estimate and has since consumed 8 times that figure. And it still isn't finished. This is not a story about a train. This is a story about what happens when a country decides that physics is a negotiating partner and refuses to accept the first offer. Today, we're counting down 8 things about Japan's bullet train that should not be possible. And by the end of this video, I promise you, you will not look at the ground beneath your feet the same way again. Let's start at number 8. Number 8. The train with no engine. When you think of a train, you picture an engine. Pistons, diesel, a roaring machine pulling carriages down a track. That's how railways have worked for 200 years. The Maglev has none of that. There is no engine on this train, not a small one. Not a hidden one, 0. Instead, the propulsion system is built entirely into the ground itself. The track, all 246 kilometers of it, is lined with electromagnetic coils. Those coils generate a traveling magnetic wave, a wave that moves forward at exactly the speed you want the train to go. And the train just follows it, pulled and pushed simultaneously by invisible magnetic forces running through the earth beneath it. Think about what that means. The vehicle has no drivetrain, no combustion. The ground is the engine. Engineers call this a linear motor, because instead of a rotating motor converting energy into circular motion, you've essentially unrolled that motor and laid it flat across hundreds of kilometers of landscape. The result is a train that doesn't accelerate in the way we understand acceleration. It doesn't push off the ground. The earth itself moves it forward. The train doesn't move. The earth pushes it. At 500 kilometers per hour, the operational target speed, the energy transfer happening between those ground coils and the train's superconducting magnets is more like a particle accelerator than a railway, which frankly is a perfect description of what the Maglev actually is. On number 7, precision at the edge of physics. Here's a question for you. How precise does a train track need to be? For a normal high-speed railway, the kind doing 300 kilometers per hour, engineers work to tolerances of about 3 to 5 millimeters. That sounds tight. It is tight. It takes skilled workers and careful surveying. The Maglev requires 1 millimeter of alignment accuracy over every 50 meters of track. Not 2 millimeters, not 1.5, 1. Now picture doing that across a route stretching nearly 300 kilometers, through mountains, under cities, across fault lines in one of the most seismically active countries on Earth. At 500 kilometers per hour, the train is covering 138 meters every single second. Any deviation in track geometry, any subtle curve, any microscopic sag creates a vibration, and at that speed, vibrations don't stay small. They amplify. They compound. A 1.5 millimeter error in one section doesn't just shake a passenger's coffee cup. It can destabilize an entire train system. So how do they build to this standard? Laser-guided construction. Every section of guideway is surveyed with optical instruments that would feel more at home in a telescope factory than on a construction site. Concrete poured to micrometric specification. Steel set not by eye, not by hand, but by instruments capable of detecting deviations that are literally invisible to the human eye. And this isn't happening in a clean warehouse. It's happening outdoors, underground, across mountainous terrain, in all weather conditions, across 60 construction sites simultaneously. This isn't engineering, it's perfection, performed under pressure, in the dark. Number 6, building beneath a living city. Tokyo is home to 14 million people in the city proper, over 37 million in the greater metropolitan area. It is the largest urban concentration on Earth. Beneath its streets runs one of the most complex subway networks ever constructed. Dozens of lines stacked on top of each other, some tunnels separated by less than 2 meters of concrete. The Maglev route begins in Tokyo, and for the first section of that route, the line travels 40 meters underground, directly beneath the city's existing infrastructure. 40 meters, that's roughly a 12-story building inverted into the earth. Below you, nothing. Above you, the foundations of department stores, the footings of elevated highways, the tunnels of active metro lines that carry millions of passengers every single day. The construction teams working this section operated under one absolute rule: zero disruption above ground. Trains above them could not be delayed. Buildings above them could not shift. Streets above them could not crack. To achieve this, engineers used a technique called underpinning, essentially building a supporting structure beneath existing foundations before removing any earth that previously supported them. Workers moved through chambers that had been painstakingly isolated from the ground movement happening elsewhere. In some sections, drilling had to stop entirely whenever a train passed overhead, because the vibration from an active metro line at certain frequencies could interfere with precision instruments trying to guide the boring below. Millions of Tokyoites walked to work, rode the subway, ate lunch. I lived their daily lives, completely unaware that 40 meters beneath their feet, teams of engineers were building the future. They never felt a thing. That was the whole point. Number 5. Machines that eat mountains. 86% of the Maglev route runs underground. Not through soft soil, not through loose sediment, through the Japanese Southern Alps, through granite, schist, and ancient volcanic rock that has been compressed and folded over 300 million years. To bore through this, they deployed tunnel boring machines, TBMs, that represent some of the largest machines ever constructed by human hands. The numbers are staggering. Each TBM is 14 meters wide, roughly the width of a 4-lane highway, 150 meters long, half the length of a standard aircraft carrier, and 4,000 metric tons in total weight. Moving one of these machines into position is itself a multi-month engineering operation. And then, after all that, after the months of positioning, the hundreds of millions of dollars spent per machine, do you know how fast they move? 15 meters per day, on a good day, through hard rock, sometimes less. The cutter heads, enormous rotating discs studded with hardened steel, grind into rock face that has been unchanged since before the dinosaurs. Those cutters wear down, constantly. Workers have to enter the machine, into the pressurized, dark, roaring front section, to replace them, in shifts, manually. The math of this project requires dozens of TBMs operating simultaneously across 60-plus construction sites, each grinding forward at geological pace, to have any hope of completing the 246 kilometers of tunnel this project demands. What they aren't cutting through a mountain, they are arguing with one, centimeter by centimeter, every single day. The biggest machines on Earth, moving slower than a bicycle, winning anyway. Number 4. The world's most dangerous construction jobs 30,000 workers. 60 active construction sites. Tunnels being bored through some of the most geologically unpredictable terrain in Asia. At the active front of any major tunnel, the section directly behind the cutting head, the air is pressurized. This is done deliberately to prevent water and unstable ground from collapsing into the bore. But pressurized environments are dangerous. Decompression sickness, the same condition that kills divers who ascend too fast, is a real and constant risk for workers in these chambers. The longer they work, the longer they need to spend in decompression before leaving. And then there's the water. Japan's Southern Alps don't just resist the drill, they bleed. Underground aquifers, fissures in rock formations, ancient water tables, all of them intersect with this tunnel route in ways that are impossible to fully predict in advance. At one point, water was flooding into active tunnel sections at 10,000 liters per minute. That's not a leak. That's a river, underground. In a space where workers are trying to operate precision machinery, managing that water required engineering entire secondary systems, pumping, treatment, environmental routing, to capture it and return it to rivers above ground without contaminating surface ecosystems. And the workers who do this, who enter these pressurized chambers, who work alongside the TBMs, and who manage water infiltration and rockfall and atmosphere control. The vast majority of them will never ride the train they built. Not because they won't be alive when it opens, but because the ticket will cost more than most can comfortably afford. The people who make this possible are rarely the people who benefit from it. That's not an engineering fact, it's a human one. Number 3. A railway that thinks the Maglev train contains 1,200 sensors per vehicle, not per train set, per vehicle. A single SC Maglev train is made up of multiple cars, which means on one complete train, you have thousands of individual sensing points, each one monitoring something specific. Temperature, vibration, magnetic field strength, gap distance to the guideway, air pressure, structural stress, electrical load. All of that data is transmitted in real time, not just to an onboard computer, but to the central control network that manages the entire line simultaneously. The engineers who designed this system didn't think of it like a train. They thought of it like a body. Every sensor is a nerve ending. Every transmission is a signal moving through a nervous system. The control center is the brain, receiving constant feedback from every point on the line and adjusting, always adjusting, in milliseconds. What does this look like in practice? If a section of guideway registers an unusual vibration signature, the system doesn't wait for a human operator to notice. It flags it, categorizes it, cross-references it against thousands of previous readings, and either resolves it automatically or escalates it based on risk level, all before the train traveling toward that section has covered another kilometer. At 500 kilometers per hour, the window between detection and response is not measured in seconds. It's measured in fractions of seconds. The system doesn't give humans enough time to react. It is the reaction. This isn't just transport. It's intelligence moving at 500 kilometers per hour. Number 2. When the system failed at 400 kilometers per hour. Here's something nobody who builds ambitious technology wants to talk about. The moment when years of calculation, billions of dollars, and thousands of working hours suddenly prove insufficient. During high-speed testing of the SC Maglev, engineers encountered what is known as a magnet quench. A superconducting magnet works by keeping certain materials at temperatures so cold, minus 269 degrees Celsius, just 4 degrees above absolute zero, that they lose all electrical resistance entirely. Current flows through them indefinitely, with zero loss. This is how the SC Maglev achieves levitation. The train's onboard superconducting magnets interact with the ground coils to lift the vehicle approximately 10 centimeters off the guideway and hold it there, continuously, at any speed. A quench is what happens when that superconductivity suddenly fails. The magnet's temperature rises above the threshold. Resistance returns instantly. The current that was flowing without friction suddenly encounters opposition, and the energy releases as heat. In a test environment, a quench means the train must stop, quickly, carefully, under control. But the question is, why did it quench? After analysis, engineers identified the cause: vibration. At extreme speeds, near 400 kilometers per hour and above, the physical oscillation of the train body was transmitting forces into the magnet mounting systems that exceeded design tolerances. Microscopically, imperceptibly to anyone outside the sensor network, but enough, at that temperature, at that precision, to matter. The response wasn't to slow the target speed. It wasn't to accept the limitation. Engineers went back and redesigned the entire magnet mounting system, the way the superconducting units are isolated from the chassis, to absorb vibration before it could reach the magnets. It worked. Then they pushed past 500 kilometers per hour, then 550. Then, in 2015, they set a world record, 603 kilometers per hour, the fastest any human being has ever traveled on the ground. Not even physics needed a second attempt. Number 1. The battle beneath the mountains. Everything we've talked about, the magnetic levitation, the sensors, the precision, the machines, the workers, all of it was preparation for the real challenge at the center of this project, the Southern Alps section. 86% of the SC Maglev route runs underground, and the deepest, most technically brutal part of that route passes through mountain rock that formed over 300 million years ago, before the Permian extinction, before the dinosaurs, before almost any animal life existed on land as we know it. This isn't soil. This isn't soft sediment you push through and line with concrete. This is ancient, folded, compressed, fractured rock that has been subjected to tectonic forces for longer than vertebrate life has existed on Earth. And beneath it, water. And enormous quantities of it, stored in natural fissures and aquifers that have no easy path to the surface. The flooding problem is not a minor construction inconvenience. At peak infiltration, tunnels were taking on 10,000 liters of water per minute. To put that in context, an Olympic swimming pool holds about 2.5 million liters. The water entering these tunnels could fill one in roughly 4 hours. Every 4 hours, continuously. While workers and machines are inside trying to work, managing this required building what is essentially a water utility company inside a mountain. Massive pumping systems, treatment infrastructure, environmental compliance measures to ensure that the water being removed doesn't simply flood downstream communities or contaminate rivers. Everything had to be captured, processed, and returned to natural waterways cleanly. 580,000 electromagnetic coils were installed in this section, manually, by workers who carried them in, positioned them, aligned them, and connected them inside cramped tunnel spaces at depth, in humid and pressurized conditions, to tolerances of a single millimeter. After more than 60 years of research, dating back to initial linear motor experiments in 1962, after $72 billion spent, After a workforce of 30,000, after 2 million test miles logged and hundreds of system failures overcome, the line connecting Tokyo to Nagoya is expected to be ready for passengers sometime around 2034 to 2035. And when it opens, the journey that currently takes 80 minutes on the existing Shinkansen, itself one of the fastest trains on Earth, will take 40 minutes. I could Tokyo to Nagoya in the time it takes to watch a TV episode. But here's the thing I want to leave you with. None of the people who started this project in 1962 will be alive to see it complete. Many of the engineers who designed its core systems have already retired. Some of the workers who built its deepest tunnels may not see it open either. This project was never built for the people building it. It was built for a version of Japan, a version of the world that doesn't exist yet. And somewhere in those mountains right now, a boring machine is grinding forward at 15 meters per day into rock that has sat undisturbed since before the age of dinosaurs. Because someone decided that the speed of human travel on Earth could be better than it is. They weren't just drilling tunnels, they were negotiating with nature. And so far, slowly, expensively, stubbornly, they are winning. That's it for today's countdown. If you want to understand how far human ambition can stretch, follow the SC Maglev. It's not just the most expensive railway ever built, it may be the most ambitious thing currently happening anywhere on Earth beneath your feet. If this one hit different, subscribe, because we've got more deep dives into the engineering projects rewriting the rules of what's possible. And until then, stay curious.